And we are now continuing with section 9.6 on representing steady state systems. Steady state systems. If you look at the last section again, representing systems, now we are on representing steady state systems. What exactly is a steady state system? I'm glad you asked. So if you remember last section, we had these transition matrices, and we raised these transition matrices to powers to represent, for example, t squared represents going from one state to another in 2 steps, and t cubed in 3 steps, and t to the 4th in 4 steps, and so on. The question is, if we raise this matrix to a higher and higher and higher power, will the matrix stabilize in the sense that you get a certain matrix, like let's say t to the 17th becomes a matrix, and then t to the 18th, t to the 19th, t to the 20th, and all the ones after that all remain the same matrix, or at least you're approaching a specific number. So the numbers are getting closer and closer. They're converging to specific numbers. If that happens, we call it a steady state system, because you reach a point where it's steady, where it stays the same from there on out, and the transition probabilities converge and remain at a specific value. Now, this doesn't always happen, so we want to have a condition for when it does. And we're going to start with the following definition. A regular transition matrix T has the property that there exists a n in n, a natural number, such that all entries of t to the n are greater than 0. So we might have a situation where your transition matrix T has, let's say, 3 states, A, B, C, and A cannot go to B directly. If A cannot go to B directly, then the entry that corresponds to the probability of A going to B in 1 step will, of course, be 0, because it's impossible. But if A can go to B in 2 steps, then T squared will not have a 0 in that case, because it's possible for A to go to B in 2 steps. So the probability is more than 0. A regular, a regular transition matrix is one that if you raise T to higher and higher powers, eventually you reach a point. There's some natural number n, whether it's 3 or 12 or 100, but there's some natural number n that eventually T to the n will have non-zero numbers in each case. That, by definition, is called a regular transition matrix. For high powers of n, a regular transition matrix converges. That means it approaches, gets really, really close to a matrix, converges to a matrix in which, and this is the key and amazingly result. I mean, it's mathematically possible to prove it, but we're not going to, but it's really, really amazing, in which all the columns have the same values. All the columns have the same values. Okay, and it says here, it's still in the box, it says in the rest of the chapter, you're only going to consider regular transition matrices. So I just want to show you an example of one. So we'll do a simple T. And here's an example. Suppose T is the following transition matrix: 0.75, 0.25, 0.2, 0.8. How do I know it's a transition matrix? Because it's square and each column adds to 1. If those two conditions hold, then you know it's a valid transition matrix. It's also a regular transition matrix because we already have a case where all of the entries are non-zero. T to the 1, non-zero. Now, obviously, if you look at this matrix, the columns are not all the same. So go to matrix, edit a 2 by 2 matrix. Let's put this in here: 0.75, 0.2, 0.25, and 0.8. Okay, so we're going to quit out of that. And then what we're going to do is we're going to raise B to, let's say, the 5th power. And when I raise this to the, I have a matrix B, but whatever matrix it is by you. When I raise it to the 5th power, I see that the columns are not the same. So let's take the same matrix and do it to the 10th power. Closer, but still not the same. Let's do it now to the 50th power. Oh yeah, even by 50, they're already the same. I wonder, let's do it to the 20th power. Were they the same then? Not quite. Let's do it to the 25th power. Not quite. Let's do it to the 30th power. Oh, we're getting so close, but not quite. How about to the 35th power? By the 35th power, oh, so close, not yet. To the 40th power. And by the 40th power, they're essentially the same within rounding error. So you see that eventually, so in this case, if I do T to the 50th, it becomes 4 over 9, 5 over 9, 4 over 9, and 5 over 9. What we see is that eventually all the columns are the same, which is an amazing, amazing, amazing result. So how do I know if I will have this result? And the answer is if it's regular. What does it mean to be regular again? It means that there's some power of T where there's no zeros, where every probability is greater than 0. And if that happens, you know for a fact that there's eventually going to be a high enough n for which the T to that power will be a matrix whose columns are the same, or at least it will converge to that scenario. We also wanted to find another definition here. We saw in the last section the election example where we had the number of people voting for candidate A and the number of people voting for candidate B. We called it a state vector because it represents the state of the system. The system is in the state of 42,000 people voting for this one and whatever the number is for that one. So we're defining the initial state vector. We'll call it S sub 0. The initial state vector S sub 0 shows the initial state of the system. Where are we starting? We have our transition probabilities, which tells us the likelihood of things moving and whatnot. But at the end of the day, if we want to actually calculate how many, then we need to know what we start with and how we transition so we can calculate what we end with. Let's do an example to illustrate that. Before we do an example, one more definition here. It says if P is a square regular transition matrix, and I personally think that the word square should be removed from that because it has to be square if it's a transition matrix in the first place. It's not wrong to say it, it's just redundant, but if P is a square regular transition matrix, there is a unique vector Q such that if you apply the transition matrix to Q, you get Q back. Because And this is the idea that eventually we want our state to converge to a specific state, a specific, how do I say this? We want the system to converge to a specific state. If I'm at that steady state, if I'm at the one that I'm going to be at forever, and I keep transitioning, then it's going to keep getting me back to the same state because it's steady. I'm going to be there forever. So I transition back to the same state. So if I take my transition matrix P and I act it on my steady, that's by the way, that's what it's called. This Q is called a steady state, or the, not a, the, because it's unique, is called the steady state vector of P. Okay, the steady state vector is the one where if I try to transition upon it, I just get back to what I started with because it's steady. From there on out, it's just going to be the same. So I can start with some state, transition to a new state, transition to a new state, transition to a new state, and keep over and over and over and over again. But eventually I will reach or converge to the steady state. In other words, if I'm interested in the long run, what's going to happen infinitely many periods from now, or just a large number of periods, I'm looking for the steady state vector. And the system, sorry, this section, one of the things that we're going to be doing is finding steady state vectors. And next section, we're going to look at equations like these and analyze them a little more in depth and come up with a mathematically rigorous way of getting the steady state vector very, very quickly. And it's actually some good fun stuff. I know, I keep saying that all math is fun, but in this case, it really is. So let's do an example. So this is back to the example we did in the last section about the dockless bicycle company math bike. So when I go back to this one, this was the one where we had the transition matrix, which connected central, inner, outer zone, central, inner, outer zone, and had a 0.5, 0.3, 0.1, 0.3, 0.35, 0.3, 0.2, 0.35, 0.6 transition matrix. Notice immediately that this is regular because already all of the entries are greater than 0. Now, according to the theory in this section, if I raise t to a high enough power, all the columns will stabilize to the same one, and that there is a steady state vector. There's a system where I have this many in central, this many in inner, this many in outer, and every period after that is just going to remain the same. Okay, and in this particular example, they're giving me a initial state vector of 110, 80, 50. So Math Bike, this company, takes 110 bikes and puts them in central, takes 80 bikes and puts them in inner, takes 50 bikes and puts them in outer. And then what happens is people ride them, and some go from C to I and I to O and O to C, and they all these transitions, and every day the number of bikes in each section is different. And the question becomes, if I wait long enough, what will I converge to? How many bikes are going to be in central? How many bikes are going to be in inner? How many bikes are going to be in outer? And stay that way from there on out. Okay, so A, calculate the likely number of bicycles in each zone of the city after 5 days using the transition matrix given in example 10. Well, I already wrote the matrix. So after 5 days, we want to transition. I'm not going to write it again. I'm just going to say we want to transition T 5 times and act on my initial state vector 110, 80, 50. So I take out my calculator, and first I'm going to edit and form a 3 by 3, which is 0.5, 0.3, 0.1, 0.3, 0.35, 0.3, 0.2, 0.35, and 0.6. Make sure I put the numbers in correctly. Okay, and we're going to quit out and then matrix, edit again. This time we want a 3 by 1. And my 3 by 1 is going to be 110, 80, and 50. And then what we're going to do is we're going to take the first one to the 5th power and multiply it by the steady state, by the initial state vector. And this gives me 65.7459, 75.789475, 98.464625. Okay, so this is the number of bikes in each section after 5 transitions, after 5 days. Of course, this is only a mathematical model. It's not going to be exact. We know we're not going to have 0.7459 bikes or anything like that. So you round. So it's about 66 bikes in central, about 76 bikes in inner, and about 98 bikes in outer after 5 transition periods. That was part A. Then part B. Find the likely steady state of math bikes. How do I find the likely steady state? Well, again, we're going to come up with a rigorous way of finding it in the next section. For now, we're just going to take t to a large enough power. If my calculator can do 100, I'll do it 100. If not, I'll lower it. There is a limit to the capabilities here. Let's take a look. This to the 100th power. Yeah, that works. Times the other one. And I get 65.26315,789, 75.7 dot dot dots, 98.9 dot dot dots. So I see that there's going to be 65 bikes, 76 bikes, and 99 bikes. So within 5 days, it already was really, really, really close to what is presumably the steady state vector. You know, within 5 days, it stabilizes and remains that way forever. C. Comment on how the owners of math bikes should reflect on their choice of the initial state vector S0 and state any limitations of this model. So what are some limitations of this model? Well, obviously the model expects that bikes are not lost or stolen or break down or better bikes come on the market. I mean, there's of course, you know, limitations of the model. We're assuming a perfect world where everything is, you know, beautiful. The probabilities, why should the probabilities be accurate? You know, if you look back at the previous section, they used, it says, by tracking their bicycles with GPS over several weeks, the company finds, and then has all these probability numbers. That's only a couple of weeks sample, which might be close to the true values, but how do we know it's the actual true value? So there's certainly limitations in the model, but it's not horrible. It's not horrible. And then we want to know about their choice of their initial state vectors. So when I look at the initial state vector, which was S0, which was 110, 80, and 50, and the steady state vector, which was 65, 76, and 99, I see that they really made not the greatest choice when it comes to how many bikes they're going to start in central and how many bikes they're going to start in outer. But inner wasn't bad. It wasn't horrible, their idea to start with 80 bikes in inner, but the 110 and 50, they grossly miscalculated how many people would, you know, be in each section and so on. So that is the example, and it's the only example in this section. We're going to go directly into the exercises now, and there actually is an investigation here, which is kind of nice, that talks about calculating the steady state vector mathematically, but in the next section we're going to do it in a nicer way anyway. So we're going to go directly to the exercises, and we're going to start with this is exercise 9H. And let's start with number 1. It says, find the long-term probability matrices for the Markov processes with these transition matrices. So A gives us a transition matrix of 0.13, 0.87, 0.71, 0.29. Again, as always, you should pause, try to figure it out yourself. So what is t to the 100 matrix? I'm going to edit a 2x2 matrix, and 0.13, 0.71, 0.87, 0.29, and take it to the 100th power. So how do I know that's high enough? As long as the columns are the same, then I know that I have reached my I've reached the point where it's a long-term probability matrix. So roughly it's 50%, it's roughly 45, 55, but not exactly. But my calculator gives me the columns the same. So I don't say, well, it's still in the process of rounding. No, I don't think it is. This should be the answer. B, this case we have t equals 0.24, 0.31, 0.42, 0.85, 0.05, 0.34, 0.15, 0.64. Notice that there's a 0, but that doesn't mean it's not regular, because just because t to the 1 has a 0 does not mean that t squared is not going to have a 0. So I put it in, and now I'm going to do this to the 100th power, and t to the 100 is approximately, looks like I have steady state, 0.141, 0.512, 0.347. 0.141, 0.512, 0.347, 0.141, 0.512, 0.347. Whoops, I'm not sure what I hit there, but okay, that should be steady state. Or the long-term probability matrix. And then C, okay, this is just busy work now, but now they give me a 4x4, 0.1, 0.6, 0.2, 0.7, 0.05, 0.2, 0.2, 0.05, 0.4, 0.05, 0.2, 0.2, and 0.45, 0.15, 0.4, 0.05. So let's edit and make a 4x4 of 0.1, 0.6, 0.2, 0.7, 0.05, 0.2, 0.2, 0.05, 0.4, 0.05, 0.2, 0.2, 0.45, 0.15, 0.4, 0.05. This is obviously regular because already everything is non-zero. And when I do this, I get 0.351, 0.104, 0.255, 0.290, and the other ones are the same because that is the property of regular transition matrices. So that takes care of question number 1. Now we move on to question number 2. A regular transition matrix T in a given Markov process is defined as follows. T equals is 3 by 3. We have 0.81, 0.1, 0.08, 0.09, 0.15, 0.5, 0.1, 0.75, 0.42. It's obviously regular. Everything is non-zero. It says let U be, and U is a vector, U1, U2, U3, be the steady state probability vector. In other words, i.e., TU is equal to U. Right? If you transition on the steady state, you get back the steady state. It says A, find U by solving a system of equations. Now, I mentioned earlier that we're going to learn in the next section a slightly more sophisticated way of finding U, but you can find U by solving a system of equations. Let's actually go ahead and do it. If T times U equals U, that means 0.81, 0.1, 0.08, 0.09, 0.15, 0.5, 0.1, 0.75, 0.42, acting on U1, U2, U3, gives you U1, U2, U3. That's just the matrix equation. Well, if I actually multiply out on the left, I get 0.81 U1 plus 0.1 U2 plus 0.08 U3 is equal to U1. I get 0.09 U1 plus 0.15 U2 plus 0.5 U3 is equal to U2. And 0.1 U1 plus 0.75 U2 plus 0.42 U3 is equal to U3. So these are now 3 equations and 3 unknowns. How am I going to solve these? Well, the easiest way is to get everything on the left. So I'm going to subtract U1 on both sides. Or for the first equation, I'm going to subtract U1, the second equation U2, the third equation U3. So I get negative 0.19 U1 plus 0.1 U2 plus 0.08 U3 equals 0. I get 0.09 U1 minus 0.85 U2 plus 0.5 U3 equals 0. And 0.1 U1 plus 0.75 U2 minus 0.58 U3 is equal to 0. So how do we solve this? Well, we know how to solve this. If you go all the way back to section 3, solving systems of equations using matrices, we know how to solve this. And one way to solve this is by rewriting it in a matrix equation and solving for the matrix U1, U3 by taking inverses. But here's the problem. If you do that, then I can tell you in advance that the determinant of your matrix is going to be 0. If you try to take the inverse, it does not exist. And the reason it does not exist is because there's an obvious solution to the situation. The obvious solution of the situation is to letting U1, U2, and U3 all be 0. If you let U1, U2, and U3 all be 0, this will automatically be true. But that's not a valid, and if you go back, of course it's true, because if you multiply by the 0 vector, you get the 0 vector back. We are looking for a non-zero vector solution. So because of that, I don't need all 3 of these, all 3 rows here. One row will automatically be redundant. It will automatically not give me information that I wouldn't have otherwise. And I can ignore it. So what I'm going to do is I'm just going to throw away any one of these 3 lines and just not use it. So because it came third, I'm just going to toss out the third line. And again, the theory behind this is a little advanced. The book doesn't really go into depth on it. And we're going to learn in the next section a more sophisticated way of doing this. So how do I solve this now? Well, I don't really need matrices to solve it, but I certainly can use matrices to solve it. What I'm going to do is I'm going to write negative 0.19, 0.1, 0.08, 0.09, negative 0.85, and 0.5, acting on U1, U2, U3 gives me 0, 0. 2 by 3, 3 by 1 gives me a 2 by 1. Everything works out. What should I do now? Well, one way of doing it is to actually, yeah, okay, this is a chapter on matrices, so we'll use matrices. But what I do want is I want a third equation. So we're going to add a third equation to this matrix, make it a 3 by 3, 3 by 1, give me a 3 by 1. But the question is, what is that third matrix going to be, a third row going to be? So what we do is we arbitrarily impose an extra condition that U1 plus U2 plus U3 is equal to 1. Okay, and the reason is because the steady state vector that we're looking for is involved in a probability process. This is a Markov chain, which is a process, a system where we're calculating likelihood of events. By requiring U1 plus U2 plus U3 to be equal to 1, we're kind of in the spirit of probabilities by remembering that every column has to add to 1. It doesn't have to be equal to 1, but and again, next section, we're going to learn a much fancier way of doing this that doesn't require any of this really confusing theory, because they don't really explain why they're doing these. They just say, hey, let's just throw this in here. But if this is the case, then we get 1, 1, 1 equals 1 like that. And now I can do that U1, U2, U3 equals negative 0.19, 0.1, 0.08, 0.09, negative 0.85, 0.5, 1, 1, 1 inverse times 0, 0, 1. Let's go ahead and do that. So second matrix, let's edit a 3 by 3, negative 0.19, 0.1, 0.08, 0.09, negative 0.85, 0.5, 1, 1, 1. And then let's edit a 3 by 1, 0, 0, 1. And then I have a inverse times what I'm calling E, and that gives me approximately 0.317, 0.274, 0.409. Hopefully you got the same thing. And in fact, if you look at the question part A, it says, let U be the steady state probability vector, not just a steady state vector, but the steady state probability vector, which is where this condition comes from, that it's not just a steady state vector, but a steady state probability vector. Now, part B says, demonstrate your answer for part A is correct by finding the long-term probability matrix. Well, the long-term probability matrix has to come back to T. So let's edit a 3 by 3. It's going to be 0.81, 0.1, 0.08, 0.09, 0.15, 0.5, 0.1, 0.75, 0.42. And let's take this matrix to the 100th power. So what is t to the 100th power? It is 0.317, 0.274, 0.409. 3 times. So what we see is the steady state probability vector is actually the same column as the columns of my eventual transition matrix raised to a high enough power. So, and I want to reiterate for the 19th time that there's an easier way of finding it, which we'll do in the next section. Question 3. It says 3 electricity providers, A, B, C, compete in a market. A survey of consumers have determined the probabilities that a person using an electricity provider in 1 year will either stay with that provider or will switch to another next year. And the probabilities are given in the following 3 by 3 matrix. We have providers A, B, C, and we have 0.8, underneath it 0.12, underneath it 0.08, does in fact add to 1. We have 0.05, 0.92, 0.03, does in fact add to 1. And then we have 0.06, 0.1, and 0.84, does in fact add to 1. At the present time, 45% of the customers are provided electricity by A. So this is not it's not how many are provided electricity by A, by what percent. So it's a probability steady state, a probability initial state vector. 25% by B and 30% by C. So we have the transition matrix and we have the initial probability steady state vector, A. Find the percentage of the customers provided by each electricity provider after 2 years. Well, 2 years means 2 transitions. So we want to take the initial probability vector, state vector, and multiply it by 2 transitions. So let's edit a 3 by 3 matrix, 0.8, 0.05, 0.06, 0.12, 0.92, 0.1, 0.08, 0.03, 0.84. And let's edit a 3 by 1 state vector, 0.45, 0.25, 0.3. And then let's do what I'm calling A, of course, A squared times what I'm calling E. And that gives me 0.34583, 0.36529, 0.28888. So we see that A has dropped, B has gone up, and C has dropped a little bit. Essentially the same, but dropped a little bit. And if you look at the column, then it might be a little surprising because 80% of the people in A stay in A. So why should it be that A has, well, actually, I'm sorry, A has, yeah, so why should it be that A has dropped so much? Hey, the math gives you what the math gives you. I'm sure you can really delve into it and see, but it is a little surprising to me, just on the surface. B, calculate the long-term percentage of customers who will be provided electricity by B. Long-term percentage. We're looking for the steady state probability vector. And we can do it in 2 ways. We can, well, so far 2 ways. One way is like we did the last problem with system of equations. And the other way is just to remember what we did in the last problem again, is that when we did the system of equations, we ended up with the same columns of the long-term matrix. And since we already have the matrix here, let's just compute t to the 100th. So a to the 100th power, and we get approximately 0.209, 0.579, 0.213 3 times. which means that the steady state probability vector, maybe we'll call it U, like the last example, is approximately 0.209, 0.579, and 0.213. And then C. By comparing the matrices T, T squared, T to the 5th, and T to the 20th, comment critically on the likelihood that the transition probabilities remain constant in the long term. Okay, so I'm going to go back here. I'm going to do T, of course, which I have here. And then I'm going to do T squared. And then I'm going to do T to the 5th. And then T to the 20th. And let's see, if I look at the first entry, 0.8 drops to 0.65 to 0.394 to 0.211. And I'm not really sure what I'm looking for here. It says comment critically on the likelihood that the transition probabilities remain constant in the long term. I don't know what they want here. Let me pause and see if I can figure it out. All right, so I didn't know what they were looking for. I did check the back. It said convergence to the long-term matrix is slow. Even when the transition probabilities remain constant, it is slow. Realistically, once the electricity providers notice the trend, they will respond to these changes quickly by changing the price or quality of their services in order to prevent customers from switching, in which case the transition probabilities are unlikely to stay constant. Those types of questions are not math questions. I mean, they're real world questions, which I'm not saying are not important, but for me, at least, you know, I love math. I can solve math problems all day long, but something like that is a slightly deeper level. I'd be impressed if a student got that. And that was yeah. So C, it's just slow convergence. I would say slow convergence. Question 4. A hire car owned by Math Car is in one of 4 possible states. A, functioning normally. B, functioning despite needing a minor repair. Minor repair but functions. C, functioning despite needing a major repair. Major repair but functions. And D is broken down. Math Car only takes a car out of service if it breaks down. Otherwise, they're going to keep using it. Minor repair, major repair, I don't care. It's working. Use it. What is the transition matrix? Well, they give it to us. They have to. There's not enough information otherwise. So the transition matrix, presumably, they don't write this, but presumably it's ABCD, ABCD, is 0.9, 0.03, 0.02, 0.05, 0, 0.85, 0.05, 0.1, 0, 0, 0.6, 0.4, and 0.96, 0, 0.04. And this represents the probabilities of the car transitioning from one state to another after a period of a month. So this is the transition from one state to another after a month. A, interpret the zeros in the matrix in the context of the problem and the entry in the 4th row, 4th column. So we want this one, this one, this one, this one, this one, and that one. What do those represent? The zeros and that one. Or to interpret them. You don't say, oh, I interpret a 0 as being a 0. That's not in the context of the problem. We need a little more than that. Okay, so what do we have here? The first 0 is from going from B to A. Well, repairs don't magically fix themselves. So if it needs a minor repair, it's not going to be normal or functioning normally until it's fixed. And it's only fixed if it breaks down. So you can't go from B to A, because the only way you can get to functioning normally is to get to breaking down. So B to A, impossible. C to A, impossible. C to B, impossible. Major repairs don't become minor repairs. So you can't go back. You can't go to from a functioning standpoint, to a better stage without getting serviced, and you're only serviced if you break down. So B to A is impossible, C to A is impossible, C to B is impossible. If you're gonna fix it, if it breaks down and you're gonna fix it, you're not gonna leave it with something that's needing a repair. You're gonna fix it completely. So you're not gonna break down and then end up being minor or major. You're only gonna break down and end up being normal. So that's why D to B and D to C is 0. And D to D, broken down, remains broken down. If it needs to be fixed, there's no guarantee that you'll fix it within the month. It might be such a major repair that it takes longer to fix, and therefore it's broken down, and a month later it's still broken down. It's a small probability, but it's non-zero. So that is, all those numbers. So we'll say A is done, even though I didn't write anything. If you're handing in homework, you should be writing what I just said, but I'm not going to write it. B, verify C, yeah, that's another typo. Verify that F is a regular Markov matrix. We got lots of zeros here. So is it a regular Markov matrix? And the answer is, it's obviously that it's yes, just from understanding what's going on here. Because can you go from normal to minor, and from minor to major, and from major to broken down? Certainly. The only thing is you can't go backwards, right? You can't go B to C or C to A, B to A or C to B. You can't go backwards. But you can get there eventually by breaking down, getting fixed, and then later having a minor or a major repair. Or a minor or major repair, breaking down, getting fixed, minor repair. Or minor becomes major, breaking down, getting fixed. So you can go back eventually. So just conceptually, I know that it's going to be regular. But if they really want me to verify it, what I'll do is I'll edit a 4x4 matrix of 0.9, 0, 0, 0.96, followed by 0.03, 0.85, 0, 0, 0.02, 0.05, 0.6, 0, 0.05, 0.1, 0.4, 0.04. And then I'm going to ask myself, what do I think is the minimum number of transitions necessary before everything is non-zero? And the answer is, if I start at B to C to D to A, 3 transitions should get me to A. So I'm going to raise it to the third power. And when I raise it to the third power, F to the third power has no zeros. So it is a valid transition, a valid regular transition probability matrix. C, math car begins business with a fleet of 500 cars in state A, 25 in B, 0 in C, 0 in D. Find how many cars are in each state after 10 months. So we want 10 transitions acting on S0. So I will take my matrix to the 10th power. And I have to input now, edit a new matrix, a 4x1 matrix of 525, 0, 0. And then multiply it by that new matrix. And that gives me, whoops, and that gives me approximately, well, that can't be, so I'm thinking I inputted incorrectly. Let me edit it again. Yes, I put 0 for the first one when it should be 500. That's a big difference. So let's go back and do the first one, which was a 4×4 to the 10th power. Okay, and then multiply it by my new matrix H. Okay, to the 10th power times H gives me 388 approximately, 70 approximately, 28 approximately, 39 approximately. D, comment on how MathCar could change their practices so that changes are made to F which improve the availability of their cars. Well, let's take a look. What could MathCar do to improve the availability of their cars? We want cars to end up being in A as much as possible. So I can't go from B to A. Well, I guess if there's a minor or a major repair, then why wait till it breaks down? Fix it immediately. Because if it's a minor repair, then if you fix it, it probably shouldn't take very long. And a major repair, if it breaks down, it'll take longer. So fix them as soon as they can. That's what I'm going to guess is what they have in the end of the book. Let's take a look. I say the changes that we're going to make are fixing things earlier. The company should repair functioning cars which need a minor or major repair before they are fully broken down to reduce the number of broken down cars. Boom. Hey, look at me. Okay, so that takes us to the end of section 9.6. We have one more section in this chapter, my favorite section, and I will see you there.